Hello guys, this is Carla and today we're going to try to understand what Riemann sums are, and it comes all from this man whose name was Bernard Riemann. He was a German mathematician who made a lot of different contributions to mathematics, but main contribution was the understanding of the definite integral. So let me try to explain you what he did in order to understand the definite integral. And okay, let's start. He started wanting to estimate the area under a curve, as we did with the integral, with definite integral. But before definite integral exists, or let's say before the mathematical definition that we know today, he started drawing rectangles under curves. So as you know, it's very easy to obtain the area of a rectangle, because all you have to do is multiply the height of the rectangle times the base of the rectangle. So by adding these areas over here, including the height of this rectangle times the base of this rectangle, he will obtain area 1. So by adding this area 1 with the area of this rectangle, the second rectangle, and then the area of the third rectangle, and then the area of the fourth rectangle, he could actually estimating the area of the under the curve. And in order to express the sum of those rectangles, he used this symbol, which is the sum of f of x I minus 1, which is actually the height of this rectangle. Let's say this point over here is f of x 0, taking in account as x0 as this point, and then times delta x, which is the base of the rectangle. So delta x actually, it is going to be b minus a over n, being a, the first point, let's call this a, b, the second point, let's call it b, and n, the number of rectangles in which we are going to divide the total area. So let's make an example. If we want to obtain the area under the curve y equals to x squared, from x equals to 1 to x equals to 3, a will be 1, x will be 3, and we will have to determine how many rectangles do we want to use in order to estimate that area. Let's say we want to estimate that area using 4 rectangles. If we divide the distance 1, 2, 3 into 4 pieces, the base of each rectangle will be 3, which is b, minus 1, which is 1, over 4, which is the number of rectangles that we want. So the base of each rectangle, as you can see, is 1/2. Okay, so we have 1/2 as the base of each rectangle, and then the height of each rectangle, which is the corresponding value of y if we substitute x. So the first, well, this is an underestimation of the area because the rectangles are under the function. So in this case, we're going to, in order to know the height, we're going to substitute 1 on the function x squared, and 1 squared, it is equals to 1. So the first rectangle, the height is 1, and the base is 1/2, okay? For the second rectangle, we're going to substitute 1.1 on the function, and 1.1 squared, it will be 2.25. I'm not quite sure that it is easy to see that, but 2.25, it will be the height of the second rectangle. The base is always the same, 1/2. And then the third rectangle, which is the substitution of 2 on the function, and if we substitute 2 squared, it will be 4. So 4 is the height of the third rectangle, and the base is also 1/2. And finally, for the height of the third rectangle, we substitute 2.5, and 2.5 square, it'll be 6.25. So 6.25 will be the height of the fourth rectangle times 1/2, which is the base. So when we add all these areas, the final answer or the final estimation is 6.75 units squared. Another method is to take in count the upper value of each of the rectangles as the height. In this case, what we have is an overestimation of the area, because we have these parts of the rectangles that are not part of the area under the curve. So on the previous example, we have an underestimation, and in this calculus we have an overestimation of the area, but the main procedure is exactly the same. We multiply the height of each rectangle times the base of each rectangle, and in this case we have that the area or the estimated area is 10.75. And the important part of Riemann is that if he realized that if we add more and more rectangles, the estimation of the area was has more accuracy, or was accurate. So this is the estimation using 10 rectangles instead of 4. So as you can see, if you use the lower method, which is the rectangles are under the curve, so you miss some small parts of the area, but very small. This is an underestimation of 7.88, and this is an overestimation using 10 rectangles, which is 9.48. So what we can think about is that the area using integrals, as we know, of the function, which is x squared times dx, from the limits of integration, which is 1 to 3, it is going to be between the underestimation, which was 7.88, and the overestimation, which was 9.48. So now, using calculus, we can know how far he was from with his estimation. So if we substitute 3 on the first function, we have 3 cubed 27 over 3 minus 1 over 3, and that is equals to 26 over 3 units squared, which is approximately the same as 8.66. So he was not so bad using the 10 rectangles estimation. And finally, what he did is that he added this symbol over here that you must remember, which is the limit as n approaches infinity. So using this, he is expressing that when we add an infinite number of rectangles, which is n rectangles approaches infinite, if we have the height of each rectangle times the base of each rectangle, we will obtain the area under the curve, which is exactly the same as the definite integral from a to b of the function times dx. As smaller dx is, as more rectangles we have. So this is what Riemann did, and I hope you have understood it.